All right, welcome back. And today we are going to do a question called in-order successor. This is a binary search tree question, and let's read it. So in-order successor, given a node in a binary search tree, may not be the root, find the next largest node in the binary search tree, also known as the in-order successor. The nodes in this binary search tree will also have a parent field to traverse up the tree. That makes it a lot easier. It means that instead of just having the left and right children, you could also go up. There's a pointer that goes up. Let's look at an example. And we already have here some example cases. For example, if you have this tree and then you want to know the in-order successor of 2, it's going to be 3. If you want the in-order successor of 4, it will be 5. All right, let's look at the iPad. It's going to be a lot more helpful. Here's a huge tree that I drew. You'll realize that there's only 2 cases in this question. There's either the case of you have to go up to find your successor or you have to go down. What do I mean by that? Okay, so whenever you choose a node, like for example, if you choose 8, then you know that the largest successor has to be here, right? Because it has to be bigger than 8. And you have to find the one that is just slightly bigger, the one that's the next, the successor, right? So how do you get a number that is bigger? You either look at your right children or it's your parent. So you either go up or down. So up or down, right? So here, obviously, the next successor is 9. We could just do that pretty obviously. So as you can see, it's in the right children. All right, let's do another example. What about this guy? What is the successor? Well, you always look at the right side, and then once you go to the right, you want to go as leftmost as possible. Because the moment you go right, all of the subtree to your right is going to be guaranteed to be bigger than yourself, right? So that rule is really important. So that's why you know that it's either you go right or you go up. And when you go up, your parent better be on the right side of you. If it's not, then it's impossible. What do I mean by that? Let me show you. For example, like number 2 here. What is the parent? The parent is the first one that is on the right side of him. So you look at your parent, you see 1, but 1 is on the left side of you, so that doesn't count. You stop the moment you go to the right, and then this is your in-order successor. Let's do another example. For example, number 4. You have no right children, so that means you have to go up. And now that you go up once, you realize it's on the left side, so that doesn't work. And then you go up again, and finally you go on the right side. So you know that this one is your successor, right? Let me do one more example. For example, if you have 9, and then you don't have a right children, so it's definitely not there. You look at your parent, you went to the left side. Okay, but that doesn't work. You go to the left side again. Well, none. I don't want to go to the left side. Once you finally go on the right side, then that is your successor. Awesome. Let's do one final example of looking at the right children. So 10, do you have a right child? Yes, you do. Let's go here. And then once you go to the right child, all you want to do is go as left as possible, because you know that anywhere from here, it becomes smaller, but you also know that you cannot go smaller than 10 because that's just how binary search tree works. Every node on the subtree to your right will be bigger. So you just keep going left until you can't. All right. So then, oh, I made a mistake. 10 cannot be 10. I mean, this will be your in-order successor. Let's change the number here so to make it valid. Let's say that's 10.5. Excellent. All right, so that's pretty much it. So let's just code it up. All right, so this is the function that we have to fill in order successor. Now, as we said before, there are 2 cases. The first case that you have to check is if you have a right children. If you don't have a right children, then you go up and you see your parent until you go to the right side of your parent. So let's do that. So first we check if we have a right node. And then if you do, that's perfect. We'll call this the current node, and then we'll take the right one. And then all you have to do is you just have to go left as far as possible. So while current left still exists, then you're gonna assign it to the left one. And then that's pretty much it. And then after that, you're done. You just return current. Okay. And then this is the other case. And then because we return here, then the other case, we don't even need an else statement. We could do this, but it's the same thing. So then in the other case, what we're going to do, we're going to look at our parent, right? So the parent, because these nodes have a pointer to the parent, this makes it way, way easier. So first you have the parent, and then you have yourself, current node. And what you want to do is you just want to go up as much as you can until you find the first parent that goes to the right side. So that means if you go to the right side, it means the parent's child, which is yourself, has to be on the left. All right. So while parent, and that means while you still have a parent to see. And then also the parent's left child is not myself, because once it is myself, I found it. All right. And then current equals parent. So as you can see, that's basically what I'm doing. Like if ever I'm going left, then I keep going left if I do the parent. But then the moment I go right, when I go to the parent, then that's my answer. Okay, parent equals parent.parent. So we just keep going up. And then at the end, you return parent. So what would happen if you choose the largest node? Like for example, on this example, if you choose 5, well, it's going to go parent, it's going to go up, and then parent is going to go up again, and then parent is going to go up again, which becomes null, which is perfect because there is no successor for the largest node. So let's see if it works. We run this, and yeah, perfectly, this works. Let's see. It's a little bit hard to see. I don't like this format. All right, cool. So as you can see, if we chose this node, then the in order successor would be 3, and we got 3 indeed. And then this in order successor would be that guy, and 5, and we got 5 indeed. All right, so that's pretty much it. So what is the time complexity of this? Well, you have to potentially traverse through all the nodes, right? It's possible that you have to traverse all the nodes. And then because of that, it's O(n). It's a linear time. And then space complexity, we didn't add anything. We didn't add any arrays. So it's O of 1. Okay. Note that the furthest that you have to travel is the height of the tree. So technically, the time complexity is O of h, which is the height. But you do know that this binary search tree is not necessarily balanced, right? It could be just a twig, like that. And then because it's a twig, then it might be a O(n) algorithm. All right, so I hope that was useful, and thank you so much. See you in the next one.